Should we get started?
Sure, sure.
Okay, so I made a quick introductions. So first, we plan to record this session today and post on YouTube. So John, if anything occurs that you want us to edit out during the session, we can do that. Just reach out to us at the end and then we'll do that. But typically we post on YouTube the next day or so.
Sure.
Okay. So today our agenda is John Mann is going to present his paper with co-author with Jordan from NYU. Farzan and Najafi talked with him at SFN and suggested that this would be very interesting to the group. So we reached out and John really kindly agreed to present. And so, John, after the meeting, we typically continue discussion on GitHub. So this is the meeting page. If you click on the discussion thread here, you go on the forum, and then you can see any questions that people may ask.
Sure, sure.
So I'll let you start. Welcome.
All right. Thank you so much for the invitation. Let's see. Can you see my screen?
We can.
Okay. Yeah, as I said, I talked to Jeremy at SFN and he talked about her on mission work. And actually, Jerome, is that the right way to pronounce your name? Jerome?
Jerome is fine. Yes.
Jerome, yeah, thank you so much. So actually, I was in the Slack group for this progress, but as a postdoc, I really want to contribute as an individual, but I feel it's too much complication between my PI and myself. So I just uh, actually I know the whole process of that OpenScope paper you guys working on is amazing. And that's such an honor for me to be here to present my work. As here is we'll be talking about dual predictive coding, which I think will be a unified framework for surprise detection in the sensory cortices. Um, I need to mention that this framework is basically considering positive and negative errors separately, and it's not really initiated by myself. It's mostly from the Keller, inspired from the other co-workers. But I really feel there is differences about the classical predictive coding and dual predictive coding. And then let me introduce gradually. Um, and then we can have make a discussion what might be impactful for the field. Okay. Um, don't delay too much. I will say, thinking about the surprise or prediction error, we have a various form of surprise. For example, when we open door and it start creaking, and we know this creaking sound is a surprise. And eventually, maybe someone later come in and fix the door, and you push the door, it doesn't creak anymore. You still feel this is kind of surprise. This is a surprise signal. It's generated from our own motion, and over the time, we can actually predict the sound um, before it comes. And similarly, when we're riding a bicycle, so Jordan mentioned the amazing bicycle in the New York winter. And when we're riding the bicycle, it's like actually we can predict the changing of the visual field, and then like a tree passing by. But if you have a truck suddenly shows up, maybe you should be surprised. Another kind of surprise is from our internal presentation. For example, when we're hearing the music, someone's press the button, stops the music, we get surprised about the missing of the sound. Or very famously, we're using the oddball, like after a sequence of normal ball, and then we should get surprised by the oddball. So in the first two examples, this surprise is mostly like a mismatched signal between our self-motor signal and the incoming sensory signal. This sensory signal can be coming from the auditory or visual cortex. For example, when we click a button, usually sometimes we can hear a sound, and over the time we're kind of expecting the sound. So one kind of mismatch is that we hear a sound, but without our own motion. We can think that's a kind of mismatch, and that can be seen as a positive prediction error. Or we having the motion, but we don't have the associated sound here. Then we can thinking about that's a negative prediction error because we have the prediction, but we don't have the matching stimulus. In the second scenario, we start to build up expectation of certain stimulus based on sensory history. And if this expectation and the incoming sensory is not matched with thinking will signal a deviant signal. Similarly, when we're hearing a sound and we expecting a sound, this response should be suppressed. But if we're only hearing a sound, this should be a positive prediction error, and then this signal might be amplified. And then another kind of deviant will be you expect a sound, but this sound doesn't come in, will be triggered as or considered as an omission. So in this talk, I will talk about these different types of surprise signal. The first time can be generally considered as corollary discharge. A second type can be considered as a perceptual prediction. But all before that, I want to talk about something about the three-factor learning rule. How you're making this positive and negative prediction error can emerge in the sensory cortex. Okay. So, so the first part is how you're modeling the biology feasible predictive coding. Traditionally, go back to the Rowe and Ballard's work, they don't even explicitly consider the error neuron. They just consider internal representation at a different layer. And if you consider this error signal, we're thinking this surprise signal, it's actually between the absolute differences between stimulus and prediction. However, in the sensory area, the baseline fire rate is super low. It's difficult for a single type of neuron that signal bidirectional change. It seems necessary to split that into positive error part and negative error part. Because this error needs to compare the prediction and stimulus, so they need to receive information from a top-down or bottom-up. However, this long-range interaction is dominantly excitatory, which is serving bad for the subtraction operation. We need some local interneuron to flip the sign such that two streams of signal can be compared. At the first glance, including negative prediction error neuron is not that intuitive, because what does that mean? That means some neuron in the sensory cortex, his activity will be negatively correlated with the sensory input. Is that true? So I don't need to introduce too much. This is like a milestone work from the Actinger 2017 from the Keller's lab. So they put the mouse in the virtual environment, and then the mouse's own movement on the treadmill will couple to the grating movement in the virtual environment. And then they put the same movement to a non-coupled training mouse where its own movement is not coupled to the visual flow. Then they can arbitrarily pausing the visual flow to introduce a mismatch signal. Surprisingly, they find both the positive response to the mismatch and the negative response to the mismatch. During the paper, they will introduce positive error neuron and negative error neuron. And then that's the starting of this dual predictive coding framework. The black bar is indicated the significance other than the baseline, suggesting there is indeed a well-distributed negative prediction error neuron in the sensory area. Importantly, they introduced the mismatch response based on the control group comparing to the mismatch to the playback halt. Another thing is when they're looking at the running onset or playback onset, there are nothing significant differences between the control group and the coupled training group and the non-coupled training group, suggesting excitatory plasticity may not play a huge role in this learning process. So based on this, we are thinking, okay, we need to have positive error neuron and negative error neuron in the cortex to make things work. But if you're thinking about a naive mouse, that doesn't fit well. Why is that? It's because we can thinking about they have a heterogeneity input from prediction signal to different neurons, and stimulus similarly have different input to a different neuron, but the local connection from interneuron to the postsynaptic excitatory neurons are more or less densely connected. Suggests that if you're thinking of population, after average, they're more likely will be the same. Same for the inhibitory stress. So for the extra mouse to perform this error calculation, they need to strengthen the inhibition from the prediction to the neuron that receiving the strongest stimulus input, similar for the neuron receiving the strongest prediction input. And then we can say, okay, the neuron performing stimulus minus prediction will call the positive prediction error neuron, and the neuron receiving the strongest prediction input can be called the negative prediction error neuron. So how can this ideal connectivity achieved through learning? So the main contribution of my work is that, yes, we can do that. And it's by very simple three-factor learning, which is just like a pre and post-synaptic activity plus a third factor. I will do a little bit math here after this slide. So if you have a question, I will allow to answer that. Feel free to pause me. I know it's like this is mostly experimental technique focus group. And also I will try to focus on the conceptual ideas. But if you have any question, just like leave directly ask me or put a question in the GitHub. I would love to answer that. So to understanding this intuitively, so the first thing is to do some simplification. As a computational neuroscience, I like to do simplification so I can do some mathematical analysis. The first part is we need to understand that we only need heterogeneity. It doesn't necessarily mean the neuron receiving the most strongest excitation from stimulus has to receive the weakest excitation from the prediction. That's totally unnecessary. Another thing is the interneuron can also receive both input from both stimulus and prediction. But I like to do some simplification. We remove some minor pathway and removing the neurons that are receiving similar stimulus excitation and prediction excitation. And then eventually the minimum case we need is just two neurons. And then we further remove the weaker pathway, and then we can get into a very simplified case where only two excitatory neuron and two interneuron and some interneuron, some connectivity from interneuron to the excitatory things, the excitatory neuron that are plastic. We can write down this formula in a standard optimization question, which is we want to minimize the decoding differences between minimize the fire rate differences between a decoder and the real error signal. So this R will be representing a decoder that telling our brain what the price currently is. So we want to minimize F, which is the firing rate between this decoder and the real surprise signal between S minus P. And this decoder will receive excitation unbiasedly from the R1 and R2. And R1, based on this diagram, will be stimulus minus some weight of inhibition of stimulus and some weight of prediction, similar for R2. So after learning, the optimal solution is 0, 1, or 1, 0, which actually means R1 will calculating stimulus minus prediction, R2 calculating prediction minus stimulus, which is positive prediction error neuron and a negative prediction error neuron. I want to explain some conceptual challenges in the predictive coding in the current field, which is the issue of representational collapse. So what does that mean? So thinking about a neural network that need to classify the cat versus dogs. So the ideal case is that we want to put the cat representation into closer to each other into some representation space, and the dogs into another subspace. To do that, we need to pull the different cats into closer to each other. But this is not sufficient. The problem is if we just pull everything together, we cannot distinguish cat versus dog anymore. If we want to distinguish cat versus dog, we need some pushing power, pushing force to split the cats versus dogs. So this can be done through Hebbian type learning, because if you know some theory, Hebbian learning can pull out the first principal component of a high-dimensional data space. This is work from Hawaga and Zanka, a previously Nature Neuroscience theoretical work. Why that is important to me? This is important because training only in the expected case is not sufficient, even for this simplified case. So doing some algebra saying X will be surprise signal, but this is sign stimulus minus prediction. Total stimulus will be S plus P. And after some calculation, or we considering is in an expected case, then we will find out the minimizing the optimal question will generating just like W1S plus W1P equal to 1, similar for W2. What does that mean? That means as long as the total inhibition balance the total excitation, the firing or the response of the error neuron will be minimized, but it's not distinguishable in the for the positive error or negative error. It's a familial case, which is not that useful for calculation. Why is that? A dead neuron can do the job. So you just don't respond to anything, and then the prediction error signal is minimized. But how does that useful for our brain? It's not. So to further distinguish and really using the error to do some cognitive tasks, we need to specify this error's contribution. How to do that is we need to consider the mismatch case. For example, when we consider stimulus bigger than P, doing some calculation, we will find out minimize this question will really help the solution space walk along this anti-diagonal to the 0, 1, suggesting the R1 becoming a positive prediction error neuron. This is a very simplified optimization problem and then can be reached through the backward propagation. Can our brain do that? Because our brain doesn't do backprop, most likely. We don't have strong evidence for that. So for the biology physical plausible learning rule, I will introduce this 3-factor learning rule. And this 3-factor is super simple. You just some value minus the real surprise signal. So noticing here, we need to know the surprise signal. Does our brain calculate that? Yes, we do. So now they have a data from the Jordan and Keller 2023. What they do is still using the mouse in the virtual environment I'm talking about and measuring the axonal input from locus coeruleus. And what they find that is this axonal activity really reflects unsigned prediction error neuron. So when there is a mismatch for the animal, the activity amplified. If you have a visual flow onset while the motion is silenced or then this similar axonal activity also trigger amplified response. And then very nicely, they have shown that the average response can be linearly dependent to the really error signal. So with that supporting the with that experimental evidence, it supports that we can think about third factor as norepinephrine or noradrenaline as a third factor to modify this Hebbian learning. So in the expected case, we have a stimulus approximately equal to P, and then we have this CT bigger than 0. Then what we will know is like updating of WS and W1P is about similar. So this similarly in the 3-factor, we will still having the error here, suggesting in the expected case, it will fast developing the EI balance, which means the total excitation and inhibition is the same for the expected case. During the mismatch case, one considers stimulus bigger than P, so the CT is less than 0, then we will have the update sign flip. However, in this case, the updating of WS is less than WP and less than 0. Then you will have this blue arrow. This is not exactly the canceling the previous progress. And then because usually the mismatch or surprise case are overwhelmed by the expected case, and we will have a zigzag fashion, eventually the synaptic weight will converge to 0, 1, which is what we actually want. So in a general case, we are talking about this as the minimized case. We can thinking about they always have like a excitation from prediction to all area neuron to the area interneuron. We can write down the similar formula, and then we can increasing the number of neuron, and we can apply the similar rule. And after similar deduction, actually we will have that the following equation. Intuitively, what does that mean? That means if you have more stimulus excitation, more positive prediction error neuron will form after learning. And if you have more stimulus inhibition, there will be more negative prediction error neurons to be formed within this same learning rule. Similar for the prediction. All right, so let's do some simulation. Theory is good. Does that work in the simulation? The answer is yes. We can start with three-factor
John?
learning rule. I have a question.
Yeah, just a clarification. The CT third factor that you said contained the unsigned prediction error factor
Yeah,
in there, right? And
yeah,
you hypothesized that this could be coming from the norepinephrine LC neurons,
yes,
right?
yes,
Um, we had a number of discussion on this. It works in my mind. It works nicely with the sensory motor mismatch from Kello's lab. But what
yeah,
happens when you have error that have much higher dimensions than 1D?
yeah, yeah. Um, very cool. So let's see. Um, okay, just a second. Um, okay, let me structure. Will be easier. Yeah, this is asked by reviewer. So the answer is so, so this learning rule 5. The surprise signal for my so this surprise signal is not necessarily the error signal. Um, the point is, in the 3D case or more general high-dimensional space, you only need a surprise signal to be a scalar. You don't need to be for the the correlus to be high-dimensional. So as long as it's locus correlus, just signal it's a surprise case or surprise case or expected case is sufficient enough to balancing the high dimensionally stimulus and prediction such that eventually in the expected case the fire rate will be depressed, and when the mismatch case the response will be amplified. Okay, this I cannot see people. I'll resharing just a second. Um, here. Yeah, does that answer your question? So the neuromodulator, in my mind, must be a scalar, but only a scalar or global signal should be sufficient to modulate local learning such that this error neuron can be formed in a high-dimensional space.
So in some ways, it's not. It's just the value of the error, and the high dimension error is learned locally. Is that right?
Yeah, yeah. So that's why actually I'm currently thinking about split the surprise and error. I try to form that surprise itself can be a neuromodulator. It's just like a single value scalar error. But however, for the error, it can be high dimension, and it can be combination of positive error and a negative error. And these two actually shouldn't cancel each other. It will talk further in the second part of the third part of the talk. Yeah.
Okay. Okay. Thank you.
Okay. All right. Okay. Nice. Yeah, it's actually exactly the the next slide. But it's hidden. I didn't expect to. Okay, anyway. All right, so in the simulation, we just like do use samples error from a truncated Gaussian distribution, and during each term, we just choose one pair of stimulus error, and then do the learning following the three-factor learning rule. And eventually, for the initial activity, it's very random, but after learning, in the expected case, where the stimulus and the prediction uh, are both existing, the red line, the activity is suppressed, while for the only surprise as only stimulus or only prediction, similar as surprise case, the activity actually be amplified. So as I mentioned, we don't need to assume the total excitation for different neurons is the same. So we can thinking about a population, someone receiving more total excitation from stimulus and prediction, some less, but this model also works fine with that. Okay. Okay. So, and then that's previously it's just a work on the ReLU neuron. Now I'm switching to the real conductant base to compartment pyramidal neuron, make it as realistic as possible. The same thing happens. So before learning, we were assuming the WP inhibition from prediction is kind of homogeneous across neuron. But after learning, the inhibition stress is really aligned with stimulus stress. Similarly, inhibition from the stimulus will align with the prediction stress. And then, what we have after learning is that in the expected case, activity goes down, while the activity in the stimulus only or the prediction only case, their activity actually will be amplified. So if you look in the histogram, that's the same. Only the expected case average fire rate decrease, but not for the other two cases. So now, because the area neuron response in the expected case is suppressed, the activity with responding stimulus only will cause that positive prediction error neuron, and in the prediction only case, we'll call that negative prediction error neuron. And from the now on, I will refer to this as the third predictive coding framework. Okay, now let's go back to the first part of correlated discharge. Yeah, okay. And then the first thing is this framework will reproduce selective modulated auditory response. So what does that mean? It's like, what if I probe with a different stimulus? So is that because thinking about in a noisy environment, so only one sound is predicted, then the sound is predicted should be suppressed. Is that true? So indeed that it is. So now we can thinking about sorting the inhibition from prediction by the expected stimulus of or like sorted by the probe stimulus. This probe stimulus is generated by shuffling the stimulus strands from the expected stimulus. So then we will see the synaptic weight from the prediction only align well with the expected stimulus. Then there is actually experiment to support that, which is from David Schneider lab at NYU. It's just like a neighboring lab. And what they have observed is that only in the expected case, the firing rate is modulated down than the probed case. So similarly, in my model, so without prediction, the response profile for the probe as expected is more or less similar. But with the prediction, here is the motion signal, so only the expected stimulus will be suppressed. And we can reproduce the modulation distribution or modulation index, and indeed, its only expected case will be suppressed. We can go back to reproduce what is a Tyler found in 2017, which is negative positive prediction error neuron in the observed from the vitro environment training. Yeah, so I will go a little bit faster because I think the latter part will be more relevant to this audience, which is kind of like expected. So sure, I can reproduce everything. And then importantly is that after learning, the sign correlation will, for some neuron, will flip. I think this is a signal of this learning process. So what does that mean? So I can give in a stimulus input that varies across different trials. Before learning, some neuron will be positively correlated all the time, but after learning, some neuron will flip its correlation after learning. This is necessary for the positive prediction error neuron and negative prediction error neuron to be formed. So can I reproduce that or can I see that in the data? That's indeed the case. So we can first, before learning, plot the correlation of single neuron. So each dot here is from a simulated data, simulated neuron, and I plot the correlation to the stimulus and the correlation with the prediction along the x and y axis, respectively. I can calculate theta, which is the angular differences between that neuron to the 45 degree. If this angular difference is 0, that means this neuron correlated similarly with the stimulus and prediction. So before learning, we have a central peak at 0, while after learning, we have two peaks emerged, suggesting one is positive prediction error neuron, another part is negative prediction error neuron, which is S minus P and P minus S. We expect in the model that some neuron once the neuron is positive correlated with stimulus, it should be negative correlated with prediction. I reanalyzed the CALAS data from 2017, and indeed, before in the non-coupled training group, so I see a single peak, but after training, I really see a double peak. This can be quantified by the Bayes interference criteria, and then showing that it's much bigger in the coupled training group. Okay. And then in the model, I can do some perturbation. So I will go past this faster. So only thing we need to know is that so if we're thinking about the brain cortex is really doing optimization problem and the circuit configuration is already at the optimum, then any kind of perturbation should decrease the mismatch signaling, and which is indeed the case. Here is the example is like inhibit the IS population, which means excite the pyramidal neurons, bisynaptic excite the neuron, or excite the IS population, which means bisynaptically inhibit the neuron. So in all these cases, mismatch response will be decreased. And then we can see it here by S perturbation, IP perturbation. Actually, I also do some NMDA suppression, but I won't discuss in detail here. All right, so that's the first part. I think this here will be more interesting and relevant here, which is about the perceptual prediction. So here, as I mentioned, in this scenario, the expectation is generated from the history of the sensory input. So having this dual predictive coding, the first thing is just saying, okay, including positive prediction error neuron and negative prediction error neuron is consistent with other phenomena. For example, omission response, which is you're giving X, 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 and then omits this stimulus input, then the circuit should generate an omission response, or it can reproduce the traditionally mismatched negativity response. It's just giving two stimulus, with one is with higher probability, another one with a lower probability. If you want interesting detail, we have our preprint online. So I want to focus here is co-contribution from NPE and PPE, which is inspired from the Jordan Ham's data previously. So what Jordan is used is like outbound paradigms, where you're giving some stimulus with 87.5 probability, while the deviant is like 1/8 probability, and then flip the redundant deviant such that the previous deviant now is redundant, and then you can further compare with random control paradigm. So what he has found is that the deviant response is bigger than the control and also bigger than the redundant. It's worth mentioning that in the traditionally mismatched negativity is really comparing the deviant with the redundant. The problem with that is we cannot really exclude the contribution of stimulus-specific adaptation or in general some fatigue mechanism, because a new stimulus is less fatigue than the repetitive stimulus. However, if we only consider the control with the deviant, then the amplified response for the deviant stimulus can only be explained by the top-down signal because for the control case, it's not adapted as well. So why I'm considering co-contribution from NPE and the PPE? So because it's thinking about in the outbound. In the outbound, we have a 3 repetition of X and Y, and comparing the X as a deviant response after certain Y. Traditionally, naively, we will think, okay, after a sequence of Y, the prediction of X is less. So we are less predicting the X. And then once the stimulus X really shows up, for the positive prediction error neuron, the decreasing as PX will trigger a bigger response for this PPX signal, PPX selected to stimulus X. However, when we considering NPEY, this is a missing part of the literature. It's like when we considering the YYYX, then we actually have the prediction of Y actually increased. If we have a negative prediction error neuron, which is positively responding to the prediction, this neuron should also signal amplifying the response. So combined together, we will consider the deviant detection signal should be conceptually a co-contribution from both NPE and PPE. So this can be easily done in the model. If you're looking at just a net response, sure, positive prediction error neuron will be bigger. For the first X, first X means X stimulus is represented as in the first repetition. Deviant X means X stimulus is represented as a deviant. Then sure, their response is big. But when we consider in deviant detection, then the PPEX and NPEY is actually signaling similar amplitude of the deviant response. So how can we distinguish that? I will suggest this should be combined with the omission response. So giving certain Y and then the omit set and see which neuron responding to is contribute to this omission. So this neuron, because PPE is actually doesn't care about the Y, but the NPEY really care about the internal prediction. And then we can do that and plotting the deviant detection or the omission differences, we can clearly see that NPEY should have both positive response in the omission paradigm and comparing the deviant X versus the first X. But for the PPX, omission difference should be negative, while the deviant detection should be positive. If we look at the scatter plot, we should observe 2 branches on this scatter plot. Such we can split NPE versus PPE. Another difference is like we can considering in the randomized outbound sequence, which is Jordan already is using. Why is that? It's like we can first split that by considering the response of the first representation of the stimulus X. Thinking about that, so for the predictor X, right? So during the first representation, then it should be similar as in the control case, because that's one of both in the control case and the first representation, it's the first time the stimulus X reach to this predictor. However, for the predictor Y, it's different. In the control case, the previous history doesn't have any information about Y or is averaged out. But in the outbound case, the previous representation is always Y. So during the first representation of X, they should have a higher activity than in the control case. Importantly is that these predictors are latent, such that you cannot directly observe it in the neuron recording. However, if you're looking at the outbound, looking at the PPX and NPY activity, this should be easier to be detected because PPX is a stimulus minus predictor X, so they should similarly reflect in activity of predictor X. So control and first should see a difference. However, for the NPEY, they really care about the activity of predictor Y, so they should have a bigger response for the first X representation. Knowing that, I reached out to Jordan, and then Jordan kindly shared his data. And then what we do is looking whether we can really find this PPEX and NPEY in his data. So here is very simple. We just first choosing deviant detector from total 326 neurons. This deviant detector is classified as have a bigger response, significantly bigger response in the deviant context than in the control context. But based on my criteria, we are considering PPEX really care about stimulus X, while NPEY don't. So we just saying if a neuron, in addition, responding significantly to the stimulus X as a control case, we will just call it putative PPEX. If it doesn't, we'll call it NPEY. So we can looking at their representation over the repetition and in different contexts, and then we can overlay them. And indeed, they both showing a very higher response in deviant case than the control case. But more importantly is that NPEY responding bigger in the first case than the control case. Another difference is we notice that is NPEY showing a stronger off response than the PPEX, suggesting maybe they're really receiving prolonged top-down prediction input. We cannot confirm that. Another thing is for the PPEX, activity only climbs up after the stimulus onset, but for the NPEY, some of the neurons seems like start to activity to accumulate before the stimulus onset. We cannot say that for sure. It seems just a straight frame before the stimulus onset. We cannot confirm that. It might worth to be further analyzed in the future data. Other things we notice that is PPE and NPE are differentiated by the orientation selectivity. For the PPE, it's just as a traditionalist neuron is have orientation selectivity, and is perfectly aligned by the stimulus X. However, for the NPEY, no, they just don't care about orientation, but they may still be selective to the top-down prediction. So here is just like talking about stimulus orientation selectivity. This can be further confirmed by aligned preferred orientation, or we can do some statistical tests on the selectivity of the variability of this orientation selectivity. All right. So in summary, so I built a three-factor learning rule. I thinking that this can enable the predictive error calculation. I'm thinking about this my unified observation from predictive coding protocol, including corollary discharge or perceptual predictive coding. And then a question for me is, sorry, so the second part is like deep predictive coding is supported by data, and we generate testable prediction. And the question for me is the other predictors necessary for the sensory cortices? Because here, the NPE is actually receiving the prediction input from top layer and have a positive correlation of prediction and within the same cortical regions. So it seems like they might serve the function of predictors at the sensory cortices. And also, it might be difficult to distinguish them with the traditional predictors, because when we're talking about stimulus absent period, like a delay period during delay match to sample, stimulus is 0, right? And then at that time, their firing rate might be similar, mathematically speaking, is similar as a predictor. So maybe in the future, we can really distinguish negative prediction error neuron versus predictor by some more strictly way. Yeah, so here is like what we have tested. We predict that if this predictive coding is really an optimized setup for the error calculation, then any perturbation should deteriorate the performance. Or we should further split them from the omission paradigm, such that there will be a ground truth. So far, it's analyzing the outbound data only. We need to rely on statistic by subtraction. One subtraction from one context to another context, it will be more difficult. The significance is less easier to be detected. All right, so here is my preprints. And also I want to talk a little bit about my future plan. So thinking about some muffin, right? So how we know it's muffin? Because it's a yellow texture and some darkened part. And we can do another muffin and muffin. And eventually we will find, okay, we have a cute Chihuahua here. And maybe we are thinking, okay, that's a surprise signal. But how we really find that, right? So do we find this surprise signal from um, color or texture? That is, we know the neuron can be selected for in the V1 or V2. So how can we say where this error is initiated if we have access to the whole brain data that collected simultaneously? So in the future, I want to study why do we really get surprise? The first question is where is this surprise can be first detected? As we know, if it's like a easier, like a feature-based or easier stimulus based surprise, sure, we have tons of data supporting that this surprise signal should be first detected in the visual cortex. But what if this is Chihuahua versus like a blueberry muffin, where it should be first detected? And when this surprise signal is detected, how is this surprise signal is transferred across regions? Can we do like simultaneous recording, doing some temporal sequence analysis to see it? And then third, when this surprise signal is transferred across different brain region, how does this surprise impact local computation? Okay, with that, I want to thank my PI, Xiaojun Wang. I also want to thank you, my collaborator, Jordan Ham and Jordan Ross. And thank you for your attention. Yeah.
Okay, it's 10:03. John, thank you so much for the presentation.
Thank you so much for invitation.
I have a couple follow-up items for next week. So one thing is we are currently finalizing a number of figures, including with some help from Lucas and others. One of these figures might benefit from your perspective, John. So I'll
Sure.
follow up the link. And then I think next week we don't still have an agenda. I might suggest we discuss the figures together again because I think there might be some updates there. If someone wants to add another items to the agenda, please reach out. Okay. Uh, thank you so much.
Thank you. Thank you for the invitation. I really enjoy it.